Here's problem 1016. A uniform rod, mass 2 kilograms, length 0.6 meters, is free to rotate by a frictionless pivot at one end. The rod is released from rest in the horizontal position. What is the magnitude of the angular acceleration of the rod at the instant it is 60 degrees below the horizontal? So let's imagine what this looks like. If we have a rod that has reached 60 degrees below the horizontal, and if we're really looking for something like angular acceleration, then we should really be thinking in terms of torque. So torque will give us angular acceleration. So this is a torque problem. And looking at this rod at this position, the force that is supplying the torque is the force of gravity, and the gravity is acting on the center of mass of the rod. So if this is the center of mass of the rod, the force of gravity is going straight down towards the center of the earth, that force being mg. It's acting on the center of mass of the rod. But if we're thinking in terms of torque, what we want to know is the line of action of this force, and then the shortest distance to that line of action from the pivot. That would be this green line here, and that shortest distance would be equal to this hypotenuse of this right triangle times the cosine of 60 degrees. So that distance, d, is going to equal r cosine 60, where r is equal to L divided by 2. So I have cosine 60 degrees. Cosine of 60 is 1/2, so this distance d is going to equal L divided by 4. Alright, nice to know, but basically we want to equate this external torque due to this gravity to the net torque on the rod. So we're going to say essentially that the torque is due to the force times the moment arm, and that's going to be equal to the force of gravity, mg, times this moment arm that we just found to be L divided by 4. Alright, so that is our torque, 1/4 mgl. Alright, but the net torque for a rod or any rotating system is the moment of inertia times the angular acceleration. And then for a rod rotating on its end, the moment of inertia is 1/3 ml squared. So this is going to be 1/3 ml squared times the angular acceleration. These two torques should be equal. So we're basically saying torque equals torque. And so we have 1/3 ml squared times the angular acceleration is equal to the actual torque exerted, which is going to be 1/4 mgl. As we look at this, the m's cancel out, and one of the l's cancel out. And solving for the angular acceleration alpha, we have alpha is equal to 3 divided by 4 g divided by L. That is our angular acceleration at this moment for this rod. And that, using the values that we have, that is equal to 3 times 9.8 over 4 times the length of the rod, which is 0.6. And what does that give us? 3 times 9.8 divided by 4 divided by 0.6. 12.25, so we'll say 12.3 radians per second squared. So that is our angular acceleration of the rod at this moment. And we may notice that is independent of the mass. So even though the mass was given in the problem, it was not needed in the problem. So it was extraneous information. The angular acceleration is 3/4 g over L, 12.3 radians per second squared for this problem.